So today I'm going to talk to you about hyperdimensional computing for regression tasks. As a few people have rightfully pointed out, oftentimes on my channel when I'm dealing with hyperdimensional computing or HDC algorithms, there are always four classification tasks as opposed to regression tasks. And then so a few people have rightfully asked the question, can you actually utilize HDC for regression tasks? And the answer is yes, you absolutely can. Should you is a different story, but you absolutely can. To me, it's like you can run Doom using potatoes, right? And then so uh, I I've stated this before, and I'll state it again in this particular instance. To me, I'm a big fan of Stephen Wolfram and computational theory. And then so if you can take out like Wolfram's computational theory, you take out the underpinnings of essentially all of my framework for my arguments within these things. But my framework for my argument is that the world is essentially and the universe is essentially computational in nature, and then so via that computational nature you could utilize the computational means of different systems and different complex systems in order for them to complete different computational tasks, and then whether or not again they are the most efficient for that is a different story as opposed to whether or not you can you run Doom on potatoes? Yes. Is running Doom via like 1,000 potatoes the most efficient way to run Doom? No, but it can be done, right? Same thing with these HDC algorithms. Can they do regression tasks? Yes. As we're going to show, would I, like in a real world situation, want to utilize HDC for regression tasks? No, but it can be done. And so that's what we're going to demonstrate within this, is utilizing HDC for continuous regression. And then so within this, how I'm going to do it is I'm going to set up, there's two different ways that I'll set up the hypervectors, but I'm going to utilize random hypervectors. I'm going to set them up randomly. There will be some adjustments that I'll make within that. And then I'm also going to introduce an L2 loss layer within this, which I'll dive into specifically. So let's first off dive into this, right? The very first thing I do is I set up the hypervectors, 10,000 random hypervector dimensions. This very first test is just straightforward test. Can I actually do it, and what will happen, right? And then the second thing that I do is I turn off binary mode within hypervectors. So if binary mode is set to true, I'm creating hypervectors between 0 and 1. In this instance, I'm creating bipolar hypervectors, so between -1 and 1 instead of between 0 and 1. And then in this first instance, I'm setting up these up very basic, right? So I'm encoding them, I'm converting the feature vectors into just straight up HDC vectors, creating the random vectors. Then I'm training the HDC regression model on the random vectors. And then essentially just computing and then measuring essentially like the difference, and then trying to improve performance based off of that. All like the cool thing with HDC to me overall is that like it's all abstractions, right? And then so like it's important to understand that like these models are training on abstractions at all times, and then at this point it's just a matter of like how abstract can you make the abstractions, and then like how many abstractions layers can you put in there, right? Like you can have the model train on an abstraction of an abstraction of an abstraction, etc. Right? And then if you handle the model right, it will be able to do that. So in this instance, that's exactly what we do. And then these are our first results. And then if you can't read these results up front, these results are terrible. Absolutely abysmal, right? Like and there's not a lot of variation in the guessing. The predictions are all wrong. They're like almost near zero. This model looks like it's like not doing anything overall, right? So if we left it here, we could show that you can functionally do something, but it wouldn't be worth like anything at all, and like it would be questionable if this is even something, right? It's just like little blips. And then so let's take it a step further here. So then again, 10,000 dimensions, and then again binary mode set to false. But then we're going to add a second layer here. So we're going to add our regularization. So our level 2 loss, which I'll show you in here. And then we're also going to beef up these hypervectors quite significantly, right? So we're going to build a vocabulary for the hypervectors. We're going to create a word hypervector dictionary within them. We're going to create encoding sentences for the hypervectors themselves. We're going to do some encoding before we actually do some predicting, and then we're going to do our predictions, and then we're going to encode our dictionary database into these vectors, all randomly, of course, but then giving the model some more framework for these hypervectors rather than just saying just create pure random hypervectors, right? And then what we get here is actually a way worse mean square error. But mean absolute error is much better, and R square error is much better because it's actually doing something, right? It's predicting something in this instance. These predictions are again terrible. The actual was 9, it predicted 3.52. The actual was 1.6, it predicted 6.33. Actual was 1, it predicted 5.11. 9.2 to 3.14, 9.0 to 3.51, and 10 to 5.515. So its predictions were bad, but they're more than 0 and more than blips of 0. So there's some life to this model, and then there's some validity to this method so far, right? We can prove that it works in theory, but not in practice, is kind of how I would evaluate this. So can we take it to the next threshold? Can we actually make it work in practice? And then so that's what I do. I like that level 2 loss, so I keep that in there, and that's just all the same. I like what I'm doing with the hypervectors, but then let's create even more logic, right? So I'll generate a bunch of hypervectors up front. Let's give it the encoding function up front. Beef up that encoding function, beef up the training function, beef up the prediction function, just essentially beef up all of these things across the board. I'm happy with how a lot of this worked, the fact that it got it to work. Now we just need to dial it, right? Give it more good in some places, trim the fat in other places, go through, and then this is absolutely beautiful, right? Our mean square error of 0.2825, which below 3 is good, right? So we're good there. And then R squared is about 80% reconstruction. So we can see our ideal line and very close to the ideal line overall, right? So, and then our predictions are generally close. So 1.73377 was the actual, the predicted was 2.09 compared to 3.00, 2.17, and then you can see some of them get really close, 2.3013 compared to 2.4665, 3.1936 compared to 2.9820, 2.764 compared to 2.54340. So that again, we're getting really close within these, which is reflecting in our graph. Some of them are a little bit further off, as you can see. That's also reflected in the graph here, that some of them are way off of the line, but generally speaking, we're on the line, right? So we're doing overall with what we would want to do, and then so this is a prediction task, right? Rather than your standard classification, this is something that a linear regression model would be able to handle very well and very efficiently overall. But you can see that we can do this for HDC as well. It is possible. It is not ideal. Again, this is the equivalent of running Doom on potatoes. It's not something that you would necessarily want to do overall. Just to this is a cool part of the trick video, I guess, is the intention. But more to me, the intention is that these things wouldn't actually work to me if computational theory didn't work, right? That's the bottom line that I take from this, is I take these experiments as further proof that computational theory is valid, right? I went into this experiment knowing that I'm going to be able to set this up. I hadn't tried to specifically utilize HDC for regression tasks in this instance before making this video, because I wasn't I just never had a reason to overall, because I never had a reason to run Doom on potatoes, but I can. And then so I knew up front when I did this that it would work. Here we are. I knew I could dial it in and everything that I needed to do. And I knew all of this because just the physics behind it, right? And predicting the physics behind it in this particular instance. And then so to me, if Wolfram's physics were wrong in this instance, then it wouldn't work. And then I'm a simple mind in that instance, and I just draw simple conclusions. And then I also utilize my eyes to look at my experiments, as I can see here, and they validate that overall for me. So then here it is. HDC for regression tasks. It is possible to do. Not recommended, but possible. Here's all the code. And then if you like this type of content, please like and subscribe. Thank you very much.